What's up, everybody? In this video, we are going to talk about scatter plots. Specifically, we're going to talk about how we can use scatter plots to comment on some real-life situations. How can we use scatter plots to model something that's happening in real life? How can we fit data on a scatter plot to help us say something intelligent about a real-life situation? That's kind of what we're after today. So first, let's just talk about scatter plots, what they are, what they look like, what the pieces of a scatter plot are. So notice this picture right here. This is a scatter plot. These are always used to model some type of real life data. So in this case, we're talking about the sugar in grams and the calories of a smoothie. Okay, sugar is on the x-axis, you'll notice, and calories of the drink are on the y-axis. Okay, and all these dots on this grid each stand for an individual drink, okay? And these are plotted the same way that we know how to plot points. So for this point up here, for instance, to get to that point, I need to go over to 70 on the x-axis and up to 320 on the y-axis. So that coordinate is located at 70, 320. Those are the coordinates for that point, which means that this smoothie, this specific one right here on this scatter plot, this point tells me that that particular smoothie has 70 grams of sugar, 70 grams of sugar, because that's what's on the x-axis, and it has 320 calories, because that's what's on the y-axis. Okay, so like I said, each one of these dots represents a different smoothie, and it is able to tell us how much sugar each of those drinks have and how much calories each of those drinks have. And again, in order to plot these, we plot them the same way we're used to plotting points. We have an x coordinate, we have a y coordinate, and in this case, the x and the y coordinates stand for something, sugar or calories. It probably won't always be that. Depends on what real life situation we're modeling. Let's talk about some features of a scatter plot. We're going to talk about this thing called correlation. It's just a descriptor of a scatter plot. So there are three different options we could have here. We could have positive correlation, we could have negative correlation, or we could have no correlation. And this should be pretty intuitive. It's pretty visual. Notice on this first graph, it says as x increases, so as I move down the x-axis, well, what are my points doing? Are they getting bigger? Are they getting smaller? Or are they not really moving in any certain pattern? Well, I notice as the x increases, if I go up on y, it looks like all these points are increasing. They are moving upwards as x increases. So as x increases, the y values also increase. That means I have a positive correlation. If I move from the left to the right and my points are going up, generally, I have a positive correlation. The same thing can be said for the negative case. As x increases in this case, as I move from the right to the left, well, now my points are going down, generally speaking. So the y's are now decreasing. As x increases here, y decreases, and now that means I have a negative correlation. So again, if I'm moving right to left and my points are going up, that means I have a positive correlation. The points are they're positively correlated, positively related. As x goes up, y also goes up. Or I could have a negative correlation. As x goes up, y goes down. Okay. Final option could be no correlation. In this case, if I move from the left to the right, well, these points just seem random. They're not really moving in any one certain direction. They're not necessarily going up. They're not necessarily going down. It just seems like a random assortment of points. So I would say these points show no pattern. They're not really going up. They're not really going down. Make sure I know how to spell pattern here. They spell no pattern. They show no pattern. That would mean that I have no correlation. They're not going up. They're not going down. There's no way to relate the data. Okay. Let's look at a couple examples of this. It says tell whether the data show a positive, negative, or no correlation. So let's just do these one at a time. Let's look at A here. I have age and vehicles owned. So a person's age on the x-axis and how many vehicles they've owned at that age. And I got a bunch of dots. And I'm looking at this, and as I move from the left to the right, it does not appear to me that these dots are showing any sort of pattern. They're not necessarily increasing with each other, and they're not necessarily decreasing with each other. So I would say that this data has no correlation. Let's look at this one. Average daily temperature and coats sold per day. So as I'm moving from the left to the right, meaning the temperature is going up, well, I can clearly see that this data is trending downwards. The Y values are going down. As the X values increase, my line would be going down like that. I have a downward trend. That means I have a negative correlation in that sense. And the very last one, I have speed in miles per hour and distance, stopping distance of a car. So that's how long it takes a car to stop going a certain speed if you just slam on the brakes. And clearly, I see that as I move from the left to the right, my data is going up. So I would say that this has a positive correlation. So that's just a little bit on scatter plots and correlation. Let's do one big problem to close out this video. And in this problem, we're going to create our own scatter plot, and we're going to try to come up with an equation for the data. Okay, so again, I got car stopping distances. I have a table here. I've got a bunch of data. I'm going to say speed is my X, stopping distance is my Y. Okay. First, let's just create a scatter plot. We're gonna get to A and B for a second, but first let's build a scatter plot. All right. There's two things that you really need to have a good scatter plot. First, you need to have labels on your axes. So let's figure that out. Well, I got my X-axis right here, and I got my Y-axis. I already labeled these what these values are going to stand for, right? The X-axis is the speed of the car. So I have speed in miles per hour of the car on the X-axis. And Y is the stopping distance. Y is the stopping distance. So let's see if I can write on my side here. Stopping. Oops. Stopping distance on the Y-axis. And again, I just labeled those by looking at the table and saying the first one's X and the second one's Y. All right, now let's get all of our data points down there. That's my first part. I need labels. Now I need the data points. In order to do the data points, I need to have a scale on each axis. I need to have a scale on the X-axis. I need to have a scale on the Y-axis. By scale, I just mean how are you gonna write your numbers? That's pretty much all I'm talking about. So on the X-axis, I need to put all these numbers down there. So I'm going to look at those numbers and say, well, those are going up by 5. So maybe going up by 5s would be a good way to draw my graph here. So I'm just going to write increments of 5. I got 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55. I don't really need to go much bigger than that because my biggest value here is 45. What about on the Ys? Well, the Ys aren't really going up in any direct pattern. But I see that I go from 27 to 196. That's a pretty big spread of data. It looks like they're going up-ish around 20 each time. So let's just go by 20s. 20, 40, 60, 80, 100, 120, 140, 160, 180, 200, 220. I don't need to go any bigger than that because, again, my biggest value here is 196, so I don't really need to go much bigger than that. Okay. All right, what's next? Well, I got my labels and I got my scales. So now I can go ahead and plot the points. Each one of these data points is a point on my scatter plot. I have an X coordinate and a Y coordinate. So I'm going to plot them one at a time. I have 10, 27, meaning I go to 10 on the X axis and a 27 on the Y axis, which maybe would be about right there. 15, 44. So I'm at 15, I go up to 44. About right there. 20, 63. Go over to 20 on the X axis, up to 63 on the Y axis. About right there. 25, 85. So there's 25, go up to 85, maybe about right there. Again, I'm not trying to be perfect here. I'm just trying to be as accurate as I can be. 30, 109. That's the next one. So I go to 30. I go up to 109, and it's about right there. 35, 136. 35, and up to 136. All right there. 40, 164. Go to 40, up to 164. And my last one, the two biggest values, 45 and 196. So I go 45, go up to about 196, maybe about right there. Okay. So there's my scatter plot. I've got my labels on the axes, I got a scale, and I got all my points plotted. So there's my scatter plot. I'm all done building it. Now I can answer these questions. Let's look at A first. It says, write the equation that models the stopping distance of the car as a function of the speed of the car. So basically, that's fancy math language for write the equation for this line. Okay? Here's how I'm going to do that. I'm going to pick two of the points for my data. It could be any of them. Doesn't matter which ones. I'm going to pick two of them, and I'm going to try to create an equation based off of those 2 points. So let's just pick the first two. 1027 and 1544. Remember, you could choose any of them. Doesn't really matter. Okay. So I choose those 2 points, and now I'm going to try to create an equation based out of those 2 points. Well, first I need to find the slope. So let's find the slope. The equation is y2 minus y1 over x2 minus x1. So I'll label. Here's x1 and y1, x2 and y2. So this is going to look like this. Y2 is 44 minus y1, which is 27. X2 is 15 minus x1, which is 10. Okay. 44 minus 27. And if you need to do that in a calculator, you can. 44 minus 27, that's 17. And 15 minus 10 is 5. Okay. So here is the slope of that line, 17 over 5. But that's not where I want to end. I want to find the equation. So I've got the slope, but I need to write an equation. Well, think about what we have. I've got the slope of the line, and I have a bunch of points that are on the line. So I can use point slope form. Y minus y1 equals m times x minus x1. I know that m is the slope. So m, my slope, 17 over 5, is going to go in there. x1 and y1, I just got to pick a point. Some point. Could be any point. So let's just pick the first one here. 10 and 27. So I'm going to put all the pieces into the equation where they need to go. It's going to be y minus y1, which is 27, equals m, which is 17 over 5, times x minus x1, which is 10. Okay. And now I'm going to try to transform this into slope-intercept form. So I got to distribute. Y minus 27 equals 17 over 5 times x is just 17 over 5x. And 17 over 5 times 10. Well, if I think about multiplying fractions, that's 17 over 5 times 10 over 1, which is 170 over 5. So I have minus 170 over 5. Okay, 170 over 5 also can probably reduce. If I put that in a calculator, 170 divided by 5, I get 34. So that actually turns into 34. One more thing, I need to add 27 to both sides of the equation. I get 17 over 5x, and then negative 34 plus 27. That gets me minus 7. So here's my equation in slope-intercept form of the line. This is the line that best fits this data. That's my equation. Well, what does it ask me to do next? It says predict the stopping distance of a car going 60 miles an hour. So let's think about what we're given. We are given a speed, 60 miles an hour. That corresponds with the x values in this situation. Speed is the x variable, and since I'm given a speed, this tells me that x needs to be 60, since x represents speed, and I am given the speed of 60 miles an hour. I want to know how long it takes the car to stop at 60 miles an hour, so I'm going to take 60 and plug it in for x. So I'm going to take my equation, 17 over 5, but I'm going to replace x with 60. 17 over 5 times 60 minus 7. And at this point, I'm just doing some calculations, okay? I'm going to do 17 over 5 times 60. So if I do that in my calculator, 17 divided by 5 times 60, I get, let's do this down here. I'm running out of room here. Let's finish this right here. I'm going to get y equals 17 over 5 times 60 is 204 minus 7. And 204 minus 7 is 197. So that means that if I'm going 60 miles an hour, it's going to take me 197 feet to stop, which is pretty astonishing when you think about it. That is a long time before your car stops. Okay? Let me make a little border here so we don't get confused. This was part B. Part C, it says predict the speed of the car if the stopping distance was 100. So again, let's think about what we have here. Stopping distance was 100. Well, stopping distance corresponds with y on my graph. Stopping distance corresponds with y. So this is giving me a y value. It's telling me that y needs to equal 100. So let's go back to our equation. Y equals 17 over 5, x minus 7. That means I need to replace y with 100. And now I'm just solving this equation for x. So I'll add 7. I get 107 equals 17 over 5x. And now I need to solve this thing for x. Well, remember we talked about if you got a fraction multiplied by your variable, quick trick to get rid of it is just multiply, flip it, and multiply. So flip it and multiply. So now I'm going to do 5 over 17 times 100. So on my calculator, I'm going to do 5 divided by 17. Multiply that by 107. Gets me about 31.47. And over here, that's just going to cancel, and I get x. Okay. So that tells me that in order for the stopping distance to be 100 feet, I would have needed to be going 31.47 miles per hour. Okay. And that looks to align pretty well with my graph. Looks pretty reasonable. Okay. All right. So that's what you need to know about scatter plots. If you have questions on your practice, let me know and I'll help you out.